Okay, this video is in regards to lesson 6.2 supplement info, the back of your work text. I throw this in because I think this is an important concept of just delving into a bit more about Riemann sums and trying to connect it to what we've done in the past with integrals. So I hope you remember that in examples 1 through 5 in section 6.2 you were asked to approximate the area under a graph using Riemann sums. So really, what is a Riemann sum? It's really the following. So given that you have this function, y equals f of x, so let me draw it here, y equals to f of x, okay? And the value of x is in some sort of interval, let's say from a to b, okay? Your goal is to find the area using a rectangle approximation method. So that was like the stuff we did, circumscribe, inscribe rectangles, midpoint, whatever, like right endpoints, left endpoints. In this case, I'm going to ask you to do it with n rectangles. But here, the width of the rectangles may vary. Okay, so for example, maybe the first width from A to wherever is that. Okay, I'm going to call that position here C sub 1. Maybe my second interval is smaller. Here we go, C sub 2. Maybe my third one is even smaller than that, C sub 3, and so on, right? Like the widths are all different. So I'll go dot, 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 dot. Now notice the height of each rectangle is also different in each of the rectangle subintervals. So you can decide which one you want to use. Perhaps in the first interval, the one in blue, I'm going to use the right endpoint. So there's my rectangle. Perhaps in my second interval here, I'm not going to use the right endpoint. I'm going to use the midpoint. Right? Maybe my third subinterval, I'm going to use, I don't know, whatever, but maybe I'll use the left one. So once again, you can vary all of the heights as well. Okay. Now when these changes are made, you are really doing a Riemann sum. Now RAM is a short form for Rectangle Approximation Method. And that's what we've really been doing. We've been doing rectangle approximations. Okay? But to generalize all the different types of rectangle approximations where the widths may vary and also the heights could be different, we have the Riemann sum. So notice f of c sub 1 is really just the y value, or the height of your first rectangle, where delta x sub 1 would really be the width of your first rectangle. So in this case, delta x sub 1 will be what I'm going to highlight right here in yellow. Similarly, f of c sub 2, this would be the height of the second rectangle. And delta x sub 2 would be the width of that second rectangle, and so on. And the idea is you're going to add up all of the rectangles up to the nth rectangle. Now I hope you've seen this notation before, because writing that long sum of things is tedious, but you can simplify it by saying the sum of k equals to 1 to n. So you're adding up all of the values of k, starting with 1, then to 2, then to 3, then to 4, all the way to n. And the representation of what you're summing is just this part here. It's f of c sub k, so that's the width of the kth interval. Sorry, not the width, my fault. The height of what I call the kth rectangle. So once again, k is just like a counter. So if k was 1, it would be the first rectangle. If k was 5, it would be the 5th rectangle. If k was 10, it would be the 10th rectangle, so on. And delta x sub k, once again, would be the width of the kth rectangle. Okay? And once again, note the Riemann sum height and widths of the rectangles may vary. So that's really the generalization of what a Riemann sum is. Just a whole bunch of rectangles added together, but not really any specific rules about what the heights could be and how the widths must be the same. Now, we know that in the previous section, lesson 6.2, we did a whole bunch of approximations, but they weren't that great. So my question to you now is, how can we find a more accurate Riemann sum? And we're going to bring back this word called limit. Stuff we did in the first days of calculus. Didn't it seem such a long time ago? But yes, it's coming back. So once again, let me just quickly draw out that function y equals f of x again. We're starting from a to b. And now let me throw in some new definitions for you. Delta x sub k, so that is the width of the rectangles. This is the length of each subinterval. Okay, so if I were to try to mirror what I did up top, from a to c sub 1, this is, c sub 1. This distance here is delta x sub 1. And then from C1 to C2, here is delta x sub 2. C2 to C3, this is delta x sub 3, and so on. Now, one new thing I want to introduce is the maximum of the delta x sub k. So the maximum delta x sub k is the length of the, well, maximum probably means the largest subinterval. Okay, so we have all these different lengths, right? We've got this length here in yellow, got this one here in blue, this one here in green. They're all different lengths. And I want the max of delta x sub k to be the largest of all these. Okay, or the width of the fattest, the rectangle. So my question to you is, how can you get a more accurate feel or accurate calculation for the area between the curve and the x-axis from A to B then? So if I want to make my Riemann sums more accurate, what can I do? I heard some of you say something. I seriously did. I think I heard some of you say, why don't we just make more rectangles so the widths become smaller and smaller? If they become smaller and smaller, then we would have a better accurate calculations for its height, and we wouldn't have as much excess or error. Good. Now, to make the width smaller and smaller, what does that actually mean? It means that the maximum value of the x sub k should what? How small can you go? If you said maybe the limit of this should go towards it being almost to 0, you are definitely correct. So to get the most accurate area calculation for the area between the curve from A to B of the function f of x, really I'm taking the limit as all these widths get closer and closer to 0 of the sum of all of the rectangles with height given by f of x and the width by this delta x. Now, what is that actually then? Look at my picture here. What did I just highlight and draw? This particular picture definitely looks like the integral from a to b of f of x dx. And that, of course, is the definite integral. And that notation is here. And notice the similarities in notation now, okay? I want you to focus on this and this. Delta x sub k. That's like my dx. F of c sub k. There's my f of x. And this limit of the sum, that's become my integral symbol. So really, that definite integral we learned in the previous unit is simply the sum of an infinite number of really, really skinny rectangles, or Riemann sum. So, if we continue on to the next page, my next question to you is, how do Riemann sums with rectangle approximations connect with this definite integral? So, once again, I'm going to draw out a picture. Let me do it up here. X, right? Whee! Y equals f of x. Starting at A, ending at B. Okay. So let's look at this concept. Okay. We know that this is just the area underneath the curve, right? But how can we connect that to this idea of now the sum of all of these rectangles? Now notice in this particular example, I said now instead of changing the width to be 0, I said let's make the number of rectangles getting closer and closer to infinity. So as many rectangles as you can. Okay? And I'm asking you to take the limit as n approach to infinity. So once again, let's make the number of rectangles be as big as we can. And I want you to find the sum of all those rectangles where this represents the height and delta x represents the width. Okay? And more particular, the height here is the right hand height. Now what do I mean by the right hand height? Okay, well, the delta x is the width, so they're all the same. So notice I'm just going to separate these into delta x. So here's delta x, here's another delta x. These widths are all the same. Delta x, and so on. Okay? So for each of these widths, I have to create a rectangle. And the question is, what do I use as the height of the rectangle? In this particular example here, I've told you that the rectangle should be the x value used for the rectangle should be a plus k times delta x. So if for our first rectangle k equals to 1, it's going to be a plus delta x, so that's a plus delta x. Can you see that I'm using the right hand endpoint to represent the height of my first rectangle? That's why it's a plus k plus delta x, or k times delta x. So when k is a counter, so when, for example, k equals to 2, that would be my second rectangle. So here is my second rectangle. The x value used to figure out the height will be a, starting at a, plus 2 delta x's. So once again, I'm using the right hand endpoint. So that formula here, or that expression that I highlighted now in both green and purple, so I'll just go green, represents the right hand height. Okay? And I can also change this idea of delta x to be more specific, since delta x represents the width of the rectangle. We know the width of equal subdivisions means taking the difference between b minus a and dividing it by n. So I could have substituted this into both of these positions, and that's how I get the final part here. Okay? Now, you may be thinking, that's fine, Danny, Mr. Lee, you used the right-hand endpoints. What if I use the left-hand end, or left-hand heights instead? How will that actually change? Well, it will change a little bit. The limit part doesn't change, so that stays the same. The limit of n approach to infinity. I still want the sum of all of these, so that doesn't change. Okay, and I still want the y values, so that doesn't change. But the question is, which y values am I now using? If you look at my picture up top, that purple rectangle now no longer would be given by that, but it would change to this, right? So what did I use as my x value for this first rectangle? I used the value of a. Not a plus delta x, but just a. Now what about the green one? How will that change? So this is my second rectangle when k equals to 2, and I use the x value at this first breakpoint. So not a plus 2 delta x's, but just a plus x. So it's always one less value of k. So notice I can still start at a, but instead of having k, I would be one less of them times delta x. And the width, of course, is delta x. Now, if you don't like that, what you could have also done was, still have the limit, still have the sum, but in this case, keep the expression the same, k, but now k doesn't start at 1, because our first rectangle I didn't add any multiples of the delta x, so k actually starts at 0. So that works too. On the AP exam, though, I believe they always look at the right hand, so you really don't need this part. Okay? Alright, so once again, here's an example of how I've converted the definite integral into this lovely expression of a limit infinite sum. Once again, how did I get this 3 over n? That's delta x, which is b minus a over n. We just leave n as n because we don't know how many rectangles we actually have. I want to have as many as possible, so that'd be 3 over n. And then I just plug it into that formula, right? F of a plus k, so this part here is your, this part here, including the 5, is your f, right? So you plug in this case, 1 as my a value, plus k, and then times 3 over n, and that's all to the power of 5. Okay? So your goal here today is to be able to go back and forth. If I give you this limit sum, you should be able to write the definite integral. If I give you the definite integral, you should be able to write the limit sum. Alright? So, I will try the first 2 with you, and I'm going to leave the rest for you to try. So if this one I'm going from the limit sum to the integral, hopefully you can see the following features. This 2 must be my a value, so I must be doing the integral from 2 to something. Now over here is 3 over n, and that supposedly is my delta x. So delta x once again is b minus a over n. Since delta x is 3 over n, and I know the a value is 2, then I should be able to figure out the value of b. What minus 2 gives you 3? Yeah, so therefore b equals to 5. So there you have it. I'm looking for the integral of 2 to 5. And now the hardest part is, what is my function here going to be? Well, in this case, I don't have an actual function. I just see f of something. So therefore, I'll just write down f of, and this part here is my x. So f of x dx. I'm done. Okay. Now for number 2, we're going the opposite way now. So I want to write this as a limit, an infinite limit, with a sum of n equals to 1 to n. And now, because I don't have a function, I'm just going to use the general form of f. But here's the thing. My a value, I'm starting at 1, so it's f of 1 plus, and I'm going to have this k times, and now what's this b or delta x? Delta x, once again, b minus a over n, in this case 4 over n. So 1 plus k times 4 over n. Okay? And then don't forget to times by the delta x, so an extra 4 over n, and close the bracket. If you wanted to make this a little bit nicer, perhaps you can write this as the limit as n approach to infinity, the sum of n equals to 1 to n, f of 1 plus 4, I don't know, 4k over n, is that nicer? Sure, times 4 over n, and you're done. Okay, let me also show you 3, because there's actually a function, and the rest I want you to do on your own. Once again, limit n approach to infinity, the sum of n equals to 1, actually it shouldn't be n equals 1, I made a mistake, my fault, k is my counter, k equals to 1 all the way to n, that makes more sense. Okay, and in this case it's not f anymore because I gave you a function, so I'm going to write down sine of, and the question is, what is my x value? Well, I'm starting at the a value of 2 plus the k times, and now once again, what's delta x? I believe it's just 2 over n, and then 2 over n. And if you wanted to write it nicer, then this is an aside, the limit, so I'm just trying to say that's equal to this now, that's my arrow, n approach to infinity, sum of k equals to 1 to n, sine of 2 plus 2k over n times 2 over n. Okay, now the rest is up to you. Press pause in this video and you work on them. When you're done, come back and press play, and voila, the answers will appear. Go ahead. See you in a bit. Did you really try these, or are you just waiting for me to give you the answer? If you're waiting for me to give you the answer, that wasn't the right move. You're trying to cheat. Please try. Here they are. Press pause and double check your answers with these.